Hi, my name is Joanna Klicka, and today I'm going to be going through homework 4 Part C. Using the final value theorem, show that with PI control, a second-order process with a measure transfer function of 1 will always reach the desired set point. To start out with this problem, we're going to draw out this scenario. So this would start with some set point going in, and from there it would be put into the controller, some amount of error, this is KC, and then GC, and then it would go to the actual process, GM, and we would see output. From there, this would be measured, which would be GM, and it would go back up into here. Now, our process is in a closed loop system, so it's going to be GCL, and it is equal to everything in the forward direction, so we're going to see GC GM divided by 1 plus everything in the closed loop system. So we have GC, this is GC, GP, GM. Now we can go through and define GC, GP, and GM. So for GC, we're going to have KC times 1 plus S tau I over S tau I. For GP, that's our function there. So we're going to have 1 plus S tau plus 1. That's times K. And finally, our measurement is 1. So now we can plug each of these up. And this is squared because it's second order. So we can plug all of these into our closed loop function, which gives us KC times 1 plus S tau I over S tau I times S tau plus 1 squared times K, and that's just the numerator. In the denominator, we are going to have the same thing, but plus 1. We can just steal this. And then we can't forget our measurement, which is just 1. It's equal to GL. Now, to evaluate this using the final value theorem, what we want to do is take the limit of this as S approaches 0, and we want to multiply by S. S times GCL, and since we are going to be deviating from steady state, we need to have a step, so we're going to have A over S, since that's the Laplace transform of a step function, and this is all going to be equal to Y at infinity. And from here we can see that these two S's here cancel out. And what we want to do now is take our big long function we have GCL written out at, and put it into our limit and take the limit of that. And so when we do this, what we're going to see is that S goes to 0. So in that case, these two denominators here are just going to go to 1. And then the other ones, when they go to 1, what we're going to end up with is 1 over S tau I. And now we still have KC, K, and A. And then on the denominator, we have 1 plus KC, K times 1 over S tau I. Now what we are going to find is that as this value here in the denominator gets bigger and bigger and bigger, the 1 becomes negligible. So we can just ignore that. And what we end up with is KCK times 1 over S tau I in both the numerator and the denominator, which means that's just 1. And then that's multiplied by A. And this demonstrates that you would reach your set point. Now we can move on to question 2. This states a system exhibiting inverse response has a process transfer function of GP equals 2 over 10s plus 1 minus 1 over 2s plus 1. Using Routh-Hurwitz analysis, determine the limits of stability for a proportional only controller in response to set point changes. Assume the measurement transfer function is 1. Okay. So as usual, the first thing we are going to do is draw out our system. So we are going to have 2 processes here. The first being 2 over 10s plus 1, and the second being negative 1 over, I think it's 2s plus 1. Yes. So for this, we are going to have a set point in. So I'm going to split each of these. These are going to split. Oops. Or come together here. And then we're going to have an output. And so we are going to call this here process 1, and this here process 2. Now these are both first order processes, so we can write this as K1 over tau 1s plus 1. And then we're just going to say minus because adding to a negative is really just subtracting. So call this K2 over tau 2s plus 1. Now we can put this as a common denominator. So we say that GP is equal to K1 times tau 2s plus 1 minus K2 times tau 1s plus 1 all over tau 1s plus 1 times tau 2s plus 1. Now if we want to look at our whole closed loop system, what we do is we put everything going in the forward direction, and we're going to have, so we're just going to multiply this by KC because we're going to have some controller. So KC times K1 tau 2s plus 1 minus K2 tau 1s plus 1 all over tau 1s plus 1 times tau 2s plus 1. And that's the numerator. And then in the denominator, we are going to have the same thing, but we're going to add 1 to it. Just like before. Steal this. And to put it in the denominator. And then, as stated, there's a measurement transfer function of 1, so if you were to multiply that, you would just get the same thing. So that doesn't need to be included. Ignore this line here that got copied down. So now, to use our stability analysis, what we really want to look at is the polynomial in the denominator of this function. So to do that, we are going to take it out of fraction form and just expand the whole thing. So to do this, we could realize that these two denominators would cancel out, and then just expand this into common denominators. So I'm going to end up with tau 1 s plus 1 times tau 2 s plus 1 plus kc k1 tau 2 s plus 1 minus kc k2 times tau 1 s plus 1. Next, we are going to expand this out. So you end up with tau 1 tau 2 s squared plus tau 1 plus tau 2 times s plus 1 plus kc k1 tau 2 s plus kc k1 minus kc k2 tau 1 times s minus kc k2. That's equal to 0. And then now we're going to group everything together by the power of s that they're associated with. So when we do that, we end up with tau 1, tau 2, s squared, plus everything that goes with an s. So tau 1 plus tau 2 plus kc k1 tau 2 minus kc k2 tau 1 times s, and then plus kc times k1 minus k2 plus 1. That's equal to 0. Now that we have this, we can do our Routh-Hurwitz analysis. So to do that, our first coefficients here are tau 1 times tau 2. Below that, we're going to put our really long one, tau 1 plus tau 2 plus kc k1 tau 2 minus kc k2 tau 1. And then up here, we're going to have kc times k1 minus k2. And this is 0 here. Now, when we do our stability analysis, what we do is we're going to multiply these two together first, multiply these two together, and divide by this giant one there. And when we do that, it simplifies out very nicely to just be kc times k1 minus k2, and these other ones just are zeros. And then we repeat this again, so we say these multiplied together, these multiplied together, and divided by this, and what you end up with is just KC. Those are there. Now what we want to do is look on our left hand column and see if any of these have the potential to be different signs. We don't want them to be negative in this case. And we can see that our second and third terms there do have the potential to be negative, so we need to find out what the limits of KC are using these. Now, if we add 1 here, it's the wrong color, right here, since I forgot that term, things will make a little bit more sense. When we come over here, we'll have KC times K1 minus K2 plus 1 is greater than 0. So we just take everything to the other side. We end up with KC is greater than or equal to negative 1 over K1 minus K2. Now if we look at our longer term here, we can write that out. We have tau 1 plus tau 2 plus KC times K1 times tau 2 minus KC times K2 times tau 1 is greater than 0. We can take everything not with a KC to the other side. Tau 2 minus KC, K2 tau 1 is greater than negative tau 1 plus tau 2. Factor out the KC, K1 tau 2 minus K2 tau 1 is greater than negative tau 1 plus tau 2. Switch that over to the other side, and we have KC is greater than negative tau 1 plus tau 2 over K1 tau 2 minus K2 tau 1. Now to really get these numbers, we can just plug in the values that we were giving in the problem statement, which lands us with negative 1 over 2 minus 1, which is just negative 1. Here we would have negative 10 plus 2 over 2 times 2 minus 1 times 10. And what that gives you is a positive 2. Yes. Which lands us with negative 1. So KC has to be greater than negative 1 and less than 2. Next, we can move on to Part 3, which states, use simulations to demonstrate the limit of stability determined in Part C2. So we can go over here to Google Colab, where I've already imported our template. So we can start by putting in our process. So GP was equal to 2 divided by 10 times S plus 1 for process 1, and then process 2 was 1 divided by 2 times S plus 1, so that our KC is equal to 1, and our closed loop is then equal to KC times GP, everything in the forward direction, divided by 1 plus KC times GP, so 1 plus everything in the closed loop system. Now we can simulate this, and we want it to be Ty. That's what we want from it. Sim GCL, our time, so lambda t is just 1. The number of steps is 1,000. Our step sizes is 0.1. Now we can plot, so fig is equal to make underscore subplots. Fig dot add scatter, x is equal to t, y is equal to y, and mode is equal to lines. Then I'm just going to update the layout. So it looks pretty. 100. smashed a button somewhere. Let's see where I went wrong. There. There it is. It looks kind of crazy right now. Maybe I was right the first time. There we go. That looks better. So now we can see what our system would look like in this situation. We can see that this is an inverse response as the system goes down first and then back up and is ultimately stable. To demonstrate the limits of stability here, I'm just going to come up and change this Kc value. So we said that the Kc needs to be between -1 and 2. So if I change this to -1, let's see what happens. Here we can see that this just goes down into nowhere and there's no signs of it coming back up to the set point that we want. And so that's on the lower end of this. The other side was that we said that Kc can't be bigger than 2. So if we make this, let's say 2.1, we can see that we also go down into somewhere that we don't want to be.